Hey everybody, welcome back to Calc 3 Online. So the plan for today is to talk about how we go about dealing with basically compositions of multivariable functions. Like i.e. we need to deal with how to do a chain rule. And it's a little bit more work, but it honestly does build off of this right here, which is your chain rule from last year. So I just want to kind of like symbolically go through this again. So the idea... a lot of times when you see chain rule in like a Calc 1 class, you'll see it this way. So they say z equals f of y, but then y is some function of x. So, you truly have some sort of composition. And when you have composition, that is going to imply that you need a chain rule. And, the chain rule is literally just the derivative of like the outer function. So, in this case, for z equal to f of y, it'd be dz dy, and then you just multiply by the derivative of the inside, like for x there, right? So then you'd be just multiplying by dy dx. And honestly, this is still very much what's happening. It's just that sometimes in order to like account for the full derivative, like all of the change in x, we need to consider adding some terms onto this. So I'm going to start off with a kind of simpler version of the chain rule in multivariable calculus. So here we have just that x is some function g of t and y is some function h of t. And then z is a function of x and y. So basically you've got composition, but your inner functions are just t. This shows up a lot like if you're doing a lot of like vector valued functions and parametric kind of stuff that we've been doing. And here it's not so bad because really to do like say the derivative of z with respect to t, you would just need to do z with respect to x and then check how x changes with t, and then just add on to that z with respect to y and then see how y changes with respect to t. And I did say this too, so notice that actually the notation is different. So in those two right there, right, you actually have an ordinary derivative because your inner functions are just single variable. You only use that partial symbol if it's multivariable, right? So this is just kind of a tree diagram to kind of help you see what's happening here. But basically we're just saying like if you want to check, z with respect to t, you need to check x like kind of along the x branch and along the y branch. And then you're basically adding those together, and that gives you the full change in z with respect to t. So this is kind of how we could use it. So you could have some function z down here, and then x and y are parametrically defined. And if I ask you what is dz dt when t equals 0, first you might want to go ahead and like input all of this if you wanted to. And then like from there you could take the derivative with respect to t, just like we've been doing it. But this can get kind of messy and it can be kind of hard to see like what, how like all the chain rules and product rules, here would be like a ton of product rules, are really all going to work out. So the idea with how we would use this trick is we can actually just take the derivative, like we can just follow this, okay? And we can do z with respect to x first. So maybe I'm going to kind of group this. So this part I'll do in green. So z with respect to x would be 2xy plus 3y to the fourth, right? And then I have to multiply by the derivative of x, like the ordinary derivative of x with respect to t. So that would just literally be 2 cosine 2t. Then I can add to this, the derivative of z with respect to y, which is going to be x squared plus 12xy cubed. And then lastly, purple, the derivative of y with respect to t would be minus sine t. And now, the idea is like that should be, this chain rule that we've just done. And you can go ahead and put in what your x and y terms are now. So you can get your final answer just by doing 2, now sine 2t, cosine t plus 3, cos t to the 4th, and then all of that times 2 cos 2t plus, go down here, sine 2t squared plus 12 sine 2t cosine t cubed, and all of that times a negative sine t. And then you can go ahead and you can like plug in t equals 0, which actually would kill a lot of things, like this term is going to go away and things like that. But this trick definitely gives us an easier way to do some of these derivatives. If we like have it in a parametric kind of xy format like this, and x and y are defined in terms of t, then we can do the derivative like we did here, and it'll like speed things up. I'm not going to go ahead and plug in t. It's fairly straightforward from there. All right, so the harder version is this one. So this is the chain rule for two independent variables. So basically what we're changing up here is instead of the function like the x and y in here being just a function of t now we have a function of like u and v for each of those in there. And you'll notice like the ordinary derivatives don't show up because there's nowhere that we have just like a single variable anymore. And but it's still structurally basically the same. Like if you want to check z with respect to u, and u is both inside of x and y, then we have to do z with x, then x with u. And that'll check the x stuff with u, basically. And then we do z with y and x with u, right? And then, likewise for v, partial z with respect to v would be z with respect to x, and then x with v, and then z with respect to y, and then partial y with respect to v. I was just looking at this and I realized there's actually a little typo here. So you've already checked x with u here, so you should be checking y with u here. So let me kind of erase that, sort of, with that trick. And then what that should say is partial of y, right? The idea is like if I check if I check how z changes with u, then you're basically checking all these branches that have something to do with u, right? And then you're just adding this and adding this. And that's like this case right here. And then this case is like you check all of the v stuff, right? And then you add this and you add this. And this can actually generalize. You can basically do this for however many branches you sort of need. So if I do, I'm just trying to think of what color is going to show up. So let's say you have like partial of u, and then with respect to like t sub I or something, basically just saying that like it's just like an arbitrary amount of those. Then you would have like partial of u with respect to like whatever that first x1 is, and then see how x1 changes with like t sub I or something, and then check u with respect to x2, and then how x2 changes with respect to ti, and plus plus plus. You just keep doing this for however many x sub n's, let's say, you have, and you'll notice the color coding that I'm trying to show you here. You'll always be able to like have sort of this kind of diagonal, I guess, effect in each term like that. these should always match. You should always be checking, the derivative of this pops up here, and you check that with respect to whatever the overall thing is. So these colors, I think, can help a little bit to see the pattern, but that's in general like how it looks. So I really just want to go through a few examples of these because it can be kind of weird, but I think once you see some examples, a lot of this is going to make sense. So here we got a very messy looking function u, which equals x to the fourth y plus y squared z cubed. And then it says x is rs e to the t, y is rs squared e to the negative t, and z is r squared s sine t. And then it says find the value of the partial of u with respect to s when r is 2, s is 1, and t equals 0. So let's first just write out what we need to do. So what we need to do is find the partial of u with respect to s, which is going to be u with respect to x. And then, because we have x, y, and z, so we're going to need 3 basically things that we're adding together. So then we're checking how x changes with s, and then we're checking how y changes with s, and lastly how z changes with s. So that's what we're going to do every time. And then, now, like, I would not go and plug these messy things in here, like in that one example that we've already done, because that's going to make the problem really messy. You have this nice format, which is going to make this derivative, and this derivative easier. So I'm going to do, maybe I'll just do all of those first. So partial of u with respect to x would just be 4x cubed y. Partial of u with respect to y would just be x to the fourth plus 2y z cubed. Okay. And then partial of u with respect to z, there's no z's in that first term, so you literally would just get 3z squared y squared. Yep. So that's just these 3 derivatives, and then we're going to be, so I'm going to put little plus signs in here. All of those are going to get multiplied by like their respective inner functions, x, y, or z, with respect to s, okay? So you would get this. Let's see, what color do I want to do? I'm going to do green. So if I do x with respect to s, I would get r e to the t, right? And then if I do y with respect to s, I'm going to get 2r s e to the negative t. And then if I do last partial of z with respect to s, I would get just r squared sine t. Okay. So now we want to find the value of this thing though when r is 2, s is 1, and t equals 0. One of these things is actually really nice because as a t equals 0, if you look over here, we got a sine t. So when you plug in 0 there, right, you're going to kill all of that stuff. So that's just going to be gone. You don't even need to worry about that. I don't think there's anything else particularly nice here. So now you just have to plug in everything else. Yeah. So we're gonna, I'm just gonna do this off to the side. So we have to plug in for x, y, and like z, right? And so what I'm gonna do is I'm gonna go up here and I'm gonna plug in my 2, 1, 0 into those, right? So just kind of a little aside, x is gonna equal 2, which is r, right? Times 1 times e to the 0. Which would equal just 2. And then y would equal basically 2 times 1 times 1, which is also 2. And then the z thing is nice because, again, we got the sign t, and the t equals 0. So z is just 0, right? So actually that also means this thing is going to go away because I had a z in there, right? So we really just need to now go plug in to the whole partial of u with respect to s is boiling down to just 4 times x cubed, which is just 2 cubed, times y, which is 2, times r, which is 2, and then e to the t, e to the 0, and that equals 128. But I was just looking through at this, and I kind of jumped the gun over here because this part is going to 0, but not that, right? So I just overlooked the fact that there's an x to the 4th in there. So I do need to add on to this also. It's going to get distributed here, right? So I would have x is 2, so 2 to the 4th, we have a 16 times 2 times r, which is 2, times s, which is 1, and then e to the negative 0. So I'm going to add to that a 64, which works out to be 92. There you go. So if you think about how messy it would be to put these in here and do out the partial, like do the partial of u with respect to s that way, I guarantee you it's way more work. So this chain rule is incredibly helpful. It really, really does speed up a ton of calculations. All right, so if you take a look at this problem, I'm going to let you pause, read it. You'll notice it's very overwhelming. There's a lot of stuff going on. It's a chain rule problem, and I want to show you kind of how I think through these sort of problems. So one of the first things, I'm very much a visual person, and I need to kind of draw what's happening. So we have these functions w, x, y, and they're saying w is defined as f of x comma t, x is x of y comma t, and y is y of s comma t. And so if you do all the proper substitutions, basically it's saying that w is going to be a function of s and t. All right, and I first want to just show you that part. So I'm going to make a little diagram over here. So we got w, and it says this is just a function of x and t. This is that it says, it's kind of one of the weird things. It says f here, not like the other ones are x and y. I kind of wish that was like a w to fit with it, but whatever. So they have w is a function of x and t, okay? And then it says x breaks down into y and t, right? And then it says y breaks down into s and t, all right? And t, there is no further splits or anything, so you get a kind of a weird tree diagram because you just basically get t just down and down and down in those other I guess in the second entry right there, right? So that's what's happening. That's the function, okay? And they say, suppose we have that x of negative 4 comma 2 is 5, and y of 7 comma 2 is negative 4, and they want you to evaluate the partial of w at 7 comma 2. So they say, in other words, evaluate the partial of w with respect to s, when s is 7 and t is 2, because w is a function of s and t. So this is an s equals 7, this is a t equals 2. And this table is enough stuff. I mean, there's extra things you don't need, but you should be able to get this from this. So the first thing I just want you to see, since we want, where did it go? We want w with respect to s, okay? This is going to be, just generally speaking, f with respect to x, okay, times x with respect to y, times y with respect to s. We never deal with the partial of the w with respect to t. So basically all this stuff over here is just being like useless information. So all these places where you see like t in here, basically you don't need those things. You're not going to need them. All right. I mean, we could even put little lines through it or something. Basically, you can ignore all the t things. So even though, if you were doing partials with respect to t, you need to like these other entries in the table. For this one, you don't. You basically are going to multiply three things. You're just going to go down this chain to get to s. So I'm actually going to start at the end here. So we know these are s and t in here, and we know y is an s and t thing. So this y, this partial of y with respect to s, needs to be the 7, 2 one, right? We've got like these extra things, 5, 2, -4, 2. We want specifically that one, right? Because the letters match up, 7 and 2. So that's, we're like 1/3 of the way there, basically. And then I'm basically going to work backwards some more here. So to keep going backwards, we know if you plug in 7, 2 to y, you get -4. So this right here is like that y, it's saying, right? So for the x one, we need the y to match, right? We want to be at the same exact point. So then really it's telling us that the x1 with respect to y that starts with a -4, which is right here, is the one I want. So that's going to be in right there. And then we just got one more. And we'll do, what color do I want to do? How about blue? So it's saying over here that if you plug in -4, 2, you'll notice all the 2's are always the same, right? Because these are just the t values. But -4, 2 equals 5. So likewise, right? That is the 5 is the x. So I want to plug that in right there. So I'm looking for the f sub x that starts with a 5, which is right here. And so then 3. And then if you just do it out, if you multiply those things, you should get, 60 is the answer. So just to show you a kind of scary problem, this was actually a bonus problem from a differential equations exam that I gave last year that I wrote up. And this is a hard problem for sure. But just to show you like a problem where we would use this kind of chain rule. So this is a style of differential equation. So basically it's something called an Euler equation. And this is true. I wrote this. He did do way too many things in math. But basically I'm doing a substitution that's going to make the whole thing work out nice. But when I do the substitution, I have to do things like this. Like this is a chain rule right here. And so I'm doing, I'm letting like ax plus b equals e to the t, and then x equals this. And then it's basically like a really, really, really messy version of, something like this one. And this one's already pretty messy. But this is probably where I feel like I used chain rule the most in math, is to solve some like really messy differential equations, honestly. I would basically try to make them easier and nicer. And believe it or not, this thing is easier and nicer. And so from here, I can get this kind of format, and this is a nice thing now. But you're not expected to know this. I just want you to see that a problem where I use chain rule, which is actually a very common trick. Most of the times, it's not like we're given this kind of stuff. We basically come up with these in math so that it can make some things when we substitute them in work out nicer, but then to do it, we have to account for that substitution using this multivariable chain rule. And like you can see it again right there. And it shows up other places too. So yeah, this is hard differential equations problem I made up. Don't think that differential equations is all like that one. All right. Just want to do some more examples here. I think I got two more I want to do. So you've got a function s of s comma t, and says f, that like s is defined as s squared minus t squared, and the t is t squared minus s squared. And f is differentiable, and we want to show that g satisfies t times a partial of g with respect to s plus s times the partial of g with respect to t equals 0. So I like this problem because it kind of gives you a taste of what I'm doing in the last one. It's like a kind of an easier sort of problem to see what I'm doing. So I'm basically going to create I'm going to like define, I'm going to say let x equals s squared minus t squared and y equal t squared minus s squared, all right? And that's basically like what the last problem was like, but these are much easier ones, okay? And then from that, I'm going to use my chain rule. So partial of g with respect to s would be f with respect to x now times x with respect to s. And then we're going to add to that f of y this time, and then y with respect to s, okay? And so partial of f with respect to x, like we don't really know because we weren't really given what it is specifically, right? It's just that f is differentiable. So we can write partial of f with respect to x, but now we do have x with respect to s, right? Which is going to be 2s, and then the minus t squared part goes away. So we have that. And then likewise, we have the partial of f with respect to y, which we don't really know, but we know it's differentiable. And then we multiply by the partial of y with respect to s. So that's going to be just minus 2s, okay? So this thing is going to go in right here, right? But I need to also get the partial of g with respect to t. So I'm going to set that up now. All right, so just by chain rule, right, we would have that. And then same kind of tricks as before. We don't really know what partial of f with respect to x is, but we know it's differentiable, so we can write that. But x with respect to t is just going to be minus 2t. And then we'll copy this down. And then partial of y with respect to t is going to be just 2t. So now we can go and plug everything in, and we'll basically be done. So we want to show that t times partial of f with respect to x times 2s plus partial of f with respect to y times minus 2s. So all of that stuff is my partial of g with respect to s. And then I add to that. All right, so that's just plugging everything in. And then if you look at what we got here, right, we have like minus 2st, really, times partial of f with respect to y. And then we have 2st times partial of f with respect to y. So those cancel, right? And then likewise for the other terms, they cancel. So all that stuff is canceling out, and it's getting 0. So this shows that this function g satisfies this weird differential equation.